Okay. Seems stuffy in here, doesn't it? Yeah, I know. It's weird. Okay, so I did send out an email. Right? Yesterday? I sent an email out. On Canvas, I put the solutions to the review. And I also noted that on that review, there were problems on polynomial functions. And so I felt like that review was a pretty good guide. I actually just finished making the exam, and I left it with the person who's going to come in and proctor it. And so that's all set. So if you can do well on that review, you should be okay. That review, remember, will only cover up through polynomials, and today we're going to cover rational functions, which you looked pretty excited about. Last class, we talked about just at the very end. Then, of course, Monday we're going to have our exam. And then I also sent out in that email, or it might have been a separate email, a link to two videos to watch. And they're actually very, I don't know. The second one, I actually do a review towards the end of it. I say this in the email. So it's really only about an hour and 15 minutes of video that I want you to watch. And yeah, so watch that on Wednesday. And then when we come back the following Monday, that's our last real lecture day. So we'll talk about the video a little bit. We'll talk a little bit about logarithms, maybe systems of equations a little bit. And then we'll talk about the exam, the final exam, and then we'll have the final on Wednesday. And that's the plan. Now, I also said that I'm going to get a third exam in there that would replace your lowest exam. Remember I said that? So I'm going to call it exam 3, even though it's going to be a replacement exam. I'm almost done with it. I'm going to email that out to you today. All right? You don't have to even look at it yet. You can wait, and it's just due on the day of the final. So when you come in here on that last Wednesday of class, make sure you bring that completed exam with you. That way I can grade it. Now, if you're happy with your 2 exams that you have now and you don't want to do that, you don't have to. All right? Does that make sense? But if you didn't do well on exam 1, or you think this exam 2 is not going to go well, then I would take care of that. Any questions on the way things are going to roll here for the next couple of weeks? Okay. Any questions on the homework that I asked you to take a look at? Any issues? Did you run into anything trying to graph those polynomials? Yes? What do you got? Let me see it.
I wasn't sure if I did it right, because I ended up having to...
Yeah, let's do that. 9x to the 5th minus x cubed. That's it right there? Okay. So, yeah, on this one, it's a polynomial because you can see it's got a degree, 5 here? So it is not factored yet. Because remember I told you last class, when it comes to polynomials, there's 2 ways you're going to see it. It's either going to be factored for you, or it's not going to be factored. This one's not factored. So that's good news in the sense that we can identify the degree and the leading coefficient right away, and that tells us our end behavior. Make sure on your cheat sheet for Monday, everyone's allowed to have a formula sheet, okay? Remember, no worked out problems, all right? Make sure you put your name on it, and you'll turn that in with the test. Last time you turned them in, but some people forgot their names on them, and it's okay, it's just I have to keep them together, and so just try and remember to put your name on your formula sheet. Okay, so on your formula sheet, I would have that table that has the end behavior, because I'm not going to provide that for you, all right? So the end behavior of this one, the left side's going to go down, the right side's going to go up. Are we all okay with that part? Yeah. All right, so now let's try and factor. So when I factor this, I can pull out, x cubed, right, GCF. And all I'm left with here is 9x squared minus 1. And I'm setting that equal to 0 to try and find the x-intercepts. So this right here, I'm going to be able to set that to 0. I actually know that when I go to that x-intercept, it's going to bounce across there. What's it going to do there? It's going to cross through. And we know that because of the 3, right? That's an odd number, so that tells you we'll cross through there. This, though, we actually need to go a little further with the factoring on that part, because that is a difference of squares. Now, it may not look like a difference of squares, but this is part of the things where you have to kind of identify, you have to be able to recognize these things. This looks like something squared minus something squared, right? So without going into too much detail, if you're still struggling with this, just talk to me after class. I can help you get this. But 9x squared minus 1 becomes 3x plus 1, 3x minus 1. And then we have equals 0. Okay, so that's our difference of squares being applied there. All right, now this is to the first power and that's to the first power. So again, talking about crossing and bouncing, we know we're going to cross here because that's odd. We'll cross here because that's odd, and we'll cross here because that's odd. So we know every x-intercept we have, we're crossing through at each one of them. Do y'all agree with that? Okay, now what are the x-intercepts? So we have to take these and set them equal to 0. So you can do x cubed equals 0, and the only number that you can cube and get 0 is 0 itself. And then here, we set that to 0, you get 3x plus 1 equals 0. Then this one you set equal to 0, 3x minus 1 equals 0. And you're going to get negative 1/3 here and positive 1/3 here. When you just move the 1 over, divide by 3, subtract 1 on both sides, divide by 3. So we have a total here of 3 x-intercepts. Now, you asked the question, so I saw what you did. You took this and you set this equal to 0, right? 9x squared minus 1. You did that, and then you decided to not do difference of squares. So you did this, and then you divided both sides by 9, and then you took the square root and you got plus or minus 1/3, right? That's what you did? This is fine. The only danger in that is whether or not you can identify the cross and the bounce from it, right? So the only way you would know it crosses or bounces from this is you would have to realize that this started out as like a quadratic, as like a squared, and it broke down to be 2 answers, which means each one of them had to be to the first power. But see, that's a little bit trickier to think that way than to just identify the difference of squares and go with each one. That make sense? Okay. So I think I've addressed your question, but I'm going to continue. I'm just going to graph it because it's a good little review of what we did last time. So now I start with my x-intercepts, right? Make sure I put these on my graph. So 0, and then 1/3 I'm just going to put here, and negative 1/3 here. Oops, I should put dots, right? And then my left behavior is down, my right behavior is up. So from this point to the left, it's down, and from this point to the right, it's up like this. And now I'm just going to connect the dots, and I make sure that I cross through at all the x-intercepts. So here I come, I try and go through, and I'm going to cross through there, come up, come down here, I cross through. Doesn't matter how low I go there, right? I'm kind of free to draw it however I want. As long as I cross through all the x-intercepts and my end behavior looks good, then we're done. Okay, that's a good question. That makes sense now? You're good?
Yeah, that's all I missed.
Yeah, kinda. Kinda. You got to do a couple of them to get comfortable with it. So we're good or no? Okay. Any other questions on the homework? I'm happy to do another one if you need to see another one. Yes? Can you read it out to me? I don't mind. What is the negative x to the what? Fifth power?
Minus 8x to the fourth power. Plus 16x to the third power.
Okay, that one looks interesting. Okay, so this one again, looks like we're going to need to do some factoring, and that we know the degree and leading coefficient to start. Pardon?
Negative 1 and 5.
Yeah, so your degree here is odd, right? Your leading coefficient, be careful, is -1, right? That's a -1 there. So that means the left side's going to do up, right side down. Okay, so it looks like this. And then we need to factor. So we need to set that equal to 0 and try and solve it. So let's see here. So did you do a GCF first? What did you pull out as a GCF? Negative x cubed? Okay, good. I was wondering if you would pull out the x cubed or negative x cubed. You can do it either way, but pulling the negative out, we like, whenever we factor a GCF out, if there's a negative on the first term, we like to pull that negative out. Just makes the rest of the problem a little easier. So let's pull a negative x cubed out, and that's going to have the effect of changing all of the signs in here. So what will I need here? X squared here plus 8x, and then here minus 16. Okay, now you said you did quadratic formula. So yeah, let's see what happens here. Be careful, because this right here is negative 16 and 8, right? A mistake you could make is maybe thinking that it's like 4 and 4 maybe, I don't know. 4 and 4 add up to be 8, but they don't multiply to be negative 16, right? They multiply to be positive 16. So that's not a correct factorization of that quadratic. So this doesn't work. Are there any other numbers that you can think of? What if you make one of those negative? Then that would work, right? But that wouldn't.
Right.
So it's no go there. And that's why you had to go to the quadratic formula, didn't you? Right? So when we go to the quadratic formula, well, here, let me just go straight to the quadratic. So this doesn't work. Now, before I do the quadratic formula, let's think about something. Because the bouncing and crossing, I think, is probably, again, becoming the issue. When I do quadratic formula on this, I'm going to either get no answers, which would mean that we get underneath the square root, we get a negative, right? We get one answer. We talked about this, the radicand, that thing under here in the formula. If this is a negative number, we have no answers. If this is 0, we get one solution. If this is a positive number, we get 2 solutions, right? So think about this. Right here, if we're trying to figure out cross and bounce, if we get 2 answers, then that should break up into 2 pieces, shouldn't it? And then each one of them would have to have what power on them? 1, right? Because it's squared, they would each have to have 1. If we have 2 answers. What if we only have 1 answer? Then it would be one of these things, right? But it would have to be squared, so it would be 2 here, so it would bounce. And if we have none of them, then we don't have an x-intercept. The only one we would have is this one. Now that's a little bit, I mean, this is kind of starting to stretch it a little bit. I think on the test, I made sure on anything I asked you to graph that it came to a quadratic, you could factor it, that you didn't have the quadratic formula come up. All right. Now there are problems on the test that you have to use a quadratic formula. Don't get me wrong. But in the polynomial part, I don't think I threw it in there. Okay, so let's do our quadratic formula on this part right here to see if we can figure out what the 2 answers are, if there are 2 answers. So let's see, negative 8 plus or minus square root. And then we square the b, right? This is b, so we square that. That's 64 minus 4 times a. What's a? 1, and then c, negative 16. All divided by 2 times 1. All right, so y'all seem to react positively to this when I said just count the number of negative signs you see. So I see 2, right? If there's an even number of negative signs, that means it's going to turn into a plus. So this is going to become negative 8 plus or minus square root 64 plus, and then what's 4 times 1 times 16? 64. So 64 plus 64 again, all over 2. 64 and 64, 128, and over 2. So you see, we're going to get 2 answers because that's a positive number. So what is root 128? You want to have that for me? 11.31, and then over 2. And so we're going to get our two X-intercepts now, right? Man, it's really stuffy in here. So I'm getting two answers. I'll just put them up here. I'm getting 1.66, okay? Or sorry, yeah, I've rounded a little bit. And the other answer I'm getting is, oh, I messed that up. Negative 9.66. Is that okay? Any questions on that? So at this point, you know you have two factors because it broke into two answers. Now you could even do this. Look, if you wanted to think through this, those are the two factors. Remember, we were trying to come up with two numbers that added up to be 8 and multiplied to be negative 16. We couldn't come up with those numbers. Well, these are actually the two numbers. If you add these up, you get negative 8, right? And if you multiply them, it'll be real close to positive 16. We rounded a little bit. All I'm trying to get you to see is that this does break down into two things. And that's why we know we're going to cross at each one of them, right? Now, why did I put the opposite in here? I put x minus 1.6, but it was positive 1.6. Yeah, the 1.6 is the answer, right? It's the answer. To get to that, we have to set this to 0. So if you set x minus 1.66 to 0, then you move the negative over, it's going to become positive. So when you go back, if you're trying to like recover these factors, it's the opposite in sign of whatever's here goes inside there. Okay, we're ready to graph, aren't we? I think. How many X-intercepts do we have? Don't forget this one. Right? We actually have 3 X-intercepts. Our X-intercepts, I'll put them up here, is 0, 1.66, and negative 9.66. And what am I going to do with all of them? Cross, cross, cross at every one of them. So zeros here, 1.66, and negative 9.66. Notice on my graph, I'm not drawing the little tick marks for like 1, 2, 3, 4, right? And negative 1, 2. I'm just making sure I represent all the X-intercepts and make sure they're in correct order. And now to the end behavior. Left side goes up, right side goes down. And then connect them all. Cross through, cross through, cross through, back down. Okay, that was a good one. Any other questions? Okay. All right. So let's do a recap of functions, the sketches, right? If I graph that, what does it look like? It's a line, right? This is a line. Now, we've already talked about this, but I want to add a little element to this. Lines are really good at representing certain things in the real world. Like, for example, if you have, let's say, the hours you work, and your pay, all right? Now, this doesn't apply to everybody, but a lot of people are hourly employees, right? It's like you clock in, you clock out, you get paid by the hour, right? So if you work 0 hours, let's say you make 20 bucks an hour, right? Then you would make no money if you work 0 hours, right? If you work 1 hour, you make what? 20 bucks? And then 2 hours, you make 40 bucks. And so this line is a representation of that real world situation, right? This lines are good for like water bills. If you pay water bills, okay, you have a certain amount you pay per gallon. Although it is tiered, like if you use too much water, they start charging you more. So it's actually for water bills, it looks like this. You start out, if you use nothing. Well, actually, if you use nothing, you still pay a service fee. So you start out here, and then you go up. Do y'all remember when cell phones were like you paid by the minute? You paid for minutes?
Yes.
Do they still do that?
I don't think so.
I don't think so. Okay. Like how long you're on the phone used to cost you money? All right. So data kind of works that way, right? All right. So look, for water, it's like you pay a certain amount, and then once you get to a certain point, it jumps up, and you actually start to pay more. So it's a steeper line. And then you get to a certain tier, and it goes even steeper. I believe for water, I don't know how many tiers there are, but I can tell you for electricity, I believe it's 5 tiers for electricity. Okay, so you pay a certain amount, then a certain amount. You can just, how many of you pay for your own water and electricity? Good. So you know what I'm talking about. I actually have an Excel spreadsheet that I made where I just type in my usage and it tiers it out, and I can predict. Now check this out. This is really cool. This is cool. Let's see if this works. I don't know if this is going to work. So this is I don't know, you may not see this, and I don't care if it comes out on camera or not. So this is, let me turn it this way. I put this thing on my, I don't know if y'all can see that, but it's like a little graph. This is the actual real-time electricity usage at my house. So like you can see every time it like jumps up, that's when the AC kicks in, right? I had to buy a device that hooks into your main power lines coming into your house in the box on the outside. Inside that box, you have to take the panel off, and it just clamps around the 2 main power leads, and then it just wirelessly connects to the cloud and gives you all this data. But it shows me, like right now my AC is on, I can tell it's on. And it's telling me that right now my current usage in my house is about equal to my average. So I average a certain amount. But the reason I'm showing this is because I can set it up for my bill, and I can put the tiers in there, like the tiers, the different tiers for the electric company, and it will estimate my bill for the month. So it starts to kind of like predict. Like right now, my estimate is $206. So, yeah, so now I'm like, yeah, exactly. So there's, in every household, there's called what we call phantom power, which is devices that are always on. And for my house, it's about 800 kilowatts, or 800 watts is running all the time. Like I can't seem to kill it off. But all right, so look, I'm going way off here. Okay, so lines, right? Lines are good at modeling certain real-world situations. Water bills, electric bills, the rate that somebody gets paid, right? Okay, so lines are valuable. We use them every day. I mean, you don't. They're in the background of life just happening, all right? But they are useful. Then we go to quadratics. Okay, so these are parabolas, right? And what are these good at modeling? Well, I gave you one specific example, didn't I? Stuff falling, right? You throw an object up in the air. But it models something else that is kind of neat. And that's just if you throw any object on Earth, just if you throw it, not drop it, but if you throw it across the room, watch this go across the board, right? Like its path across the board was parabolic. It's a parabola. So any object that's launched into the air, baseball, basketball, it all, like, so when someone's sitting there, y'all love Steph Curry, right? No, I'm kidding. Okay, whoever you like, if you even like basketball, shoot the ball. There is a parabola, right? Automatically, there's some f of x equals ax squared plus bx plus c. That's actually going to show you where that path is going to be. In fact, if you look at history, you know, back when there were castles, you know, we love to attack one another, right, humans? We love this. So, you know, you start lobbing like fireballs and arrows and stuff into this castle because you want all their food and everything else, right? So there was a point at which we understood that there's a parabola behind this, right? F of x equals that. And then what we could do is we could predict this point, right? And that point's the X-intercept, right? So you could actually determine where it's going to land. And then you become more accurate instead of just like randomly throwing stuff. So warfare is a great motivator for technology, isn't it?
Absolutely.
Okay, so parabolas are good for falling objects, anything that goes up, down, or if you turn the parabola around, you know, it can go down then up. But it's not good for other things, like, let's say you take time, and let's say the value of your home. Now, I know not everyone here owns a house, but if you do at some point own a home, what you'll realize is that you buy your house for your purchase price, and that's the value of your home. Whatever you're willing to pay is how much it's worth, right? So that's the value of your home. And then after that, it's really up to the market. It's whether or not your neighbors are taking care of their houses. There's a lot of factors that determine the value of your home. So straight line, no good, right? Parabola, up and down or down then up, you would hope for that. Maybe like that, you know, that'd be great.
Yeah.
But more likely, it's something that's going to fluctuate, almost like stock market, you know, and you're hoping for over time, you know, you're there for 30 years, and you're hoping that by the time you sell the home, right, or die and give it to your kids, whatever it is, right, that value is higher than what you bought it for, and adjusted for inflation, that you're going to make money. That's why they say owning a home is an investment that you're hoping to get money back at the end for it. But this is not a line, this is not a parabola, right? This is more like a polynomial function, isn't it? Now, we don't have the end behavior up and down, but in the middle, it's got that fluctuation. So polynomials, I'm just going to put polynomials are good for this, are really good for things like that, all right? So rational functions, that's what we're going to talk about today. Rational functions are good at modeling other things that none of these can do. So let me start this with, see if anybody can name this. Y'all like movie quotes? Yeah. Okay, so let's see if you can get this movie quote. And I may mess it up a little bit, but the general idea is, let me make sure I get it right here. Okay, on a long enough timeline, the survival rate for everything drops to 0. That's a quote from a movie. On a long enough timeline, the survival rate for everything drops to 0. Anyone know that movie?
Were we alive?
I hope so. I hope so. I don't know when it came out. I'll give you a hint for the movie. Brad Pitt's in the movie. Fight Club. It's Fight Club. How many of you have seen Fight Club? Show of hands. Okay. So I'm not saying that I love the movie, but that's the quote. So in the movie, one of the characters, I think it's Ed Norton Jr. He's like the main character. Brad Pitt's also in the movie. But he's an insurance adjuster. So basically what they do is they go and they look at accidents, and they say, okay, we've got bad brake pads in the car, there's something wrong, and they say, okay, what's the probability that someone's going to die in an accident? And then, so they take the number of cars out there, they multiply it by the probability that the car is going to fail, and they multiply that by what they're going to pay out to the family in an insurance claim for their family member dying, right? Make sense? Then they take that number and they compare it to another number, which is the cost of a recall. Because it costs companies a lot of money to bring all these cars in and to do a recall, and they figure out which is larger. So like, if it's cheaper to just pay out the families, then they won't do a recall. Right? It is crazy. But that, in the movie, that's his job, is to go out there and look at the accidents and stuff. But he says that on a long enough timeline, the survival rate for everything drops to 0. So let's just see what that quote means. Here's time, and here's survival rate. And let's just take like your average human being, all right? And let's talk about the probability. Let's say that they're born, right? Then the probability that they're alive at the moment they're born is 100%. They are alive. We're assuming somebody is born alive. And we're not going to talk about when life begins and all that. No, we're not getting into that right now. Let's just assume time 0, somebody is alive, right? So what happens over time? What's the probability that somebody's going to live to, let's say, see their first birthday? We'll put this in years. What's the probability that somebody's going to live the first year? Probably pretty good, right? Now, there are a lot of infant things you have to worry about, but I would say the probability that somebody lives the first year is pretty good, right? Can't say 100%, right? This is like 100%, all right? Can't say 100%, but you can say it's pretty high, in the 90s probably. Now, what's the probability that they're going to live to be 10? Well, still pretty good, right? Still pretty good. It's probably less than the chance that they're going to live to be 1 though, right? Now, what's the probability that they're going to live to be 50? And now we start dropping down, don't we? Okay, so now we start dropping, right? Now, sometimes it matters, male, females. Females usually live longer in America and blah, 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 but I won't get into that. Okay, so this is where things start to get interesting. Let me move this out of here. So what is the probability that somebody is going to live to be 100? That the average person can live to be 100? What's the probability? It's pretty small, right? In fact, today, at 6 o'clock, we're meeting my wife's grandfather is turning 100 today, and we are going to his 100th birthday. So, but he's in a minority there. Not many people will live to be 100, right? What's weird about that is we're going to go visit, we're going to have his 100th birthday at the hospital because his son is like almost on his deathbed. Like, it's weird. Like, the son Grandpa might outlive his own. He's already outlived one of his kids. He might outlive the next one. Interesting. Okay, so what is the probability that a person will live to be 120? You think it's pretty small percent? I don't know if anyone has ever lived to be 120. 124 is the record? I don't know. We could look it up, but... So can we say really small? So look at these numbers. These numbers, like if this was 0.5, that would be 50%, right? If this right here is like 0.001, that would be like 0.1%. That means like 1/10% of people live to be 100. Not 1%, 1/10 of 1% live to be 100. Now 120, you're probably talking even smaller, right? Like 0.000001 maybe, like that? What's the probability that somebody lives to be 200? Now this is why things get interesting. We're talking about probabilities, right? We're not talking about has it ever happened? Is it possible? Just because something has never happened does not mean that it is not possible. I mean, look at, if you would have gone back in history, let's say 300 years ago, and talked about people living to be 100, they would have told you 0, right? Because it just medically we weren't there, right? We couldn't not push the human body out that far. We're getting better and better. I don't know why we want to, but there's enough of us around. We do need some attrition, don't we? Okay, so So we have this dropping down. When you get to 200, you cannot say 0. It has to be, you have to leave open the opportunity for it to occur. And so it's got to be a small number, right? Maybe it's like 0.00000000000000000000000000000001, right? But that is a number, right? It's not 0. This is a tiny number, but it's not 0. Yes? Okay, so let's get crazy here and let's go out to 2,000. How about 2,000 years old? Still can't be 0. Okay, you have to put 0.00, and maybe there's 10,000 zeros and then a 1. But the point is, that point is just slightly above the x-axis. So what you wind up getting is something like this, a graph that starts to dive down towards 0. Oh, wow, didn't mean that to happen. Right, like this, but it never actually touches the x-axis. And so we need to somehow represent that. So what we do is we put like a dotted line out here. And this dotted line is what we call a horizontal this is a weird word. I know how to spell it because I've written it many times. This is called a horizontal asymptote. It's you don't have to, this is silent P, asymptote. Horizontal, meaning like a horizontal line. What it is, this horizontal dotted line, look at it, I like to look at it this way. It's like a magnet. It's pulling the graph towards it, but it's never actually allowing the graph to touch it. Make sense? Okay, lines don't do this. Parabolas don't do this. Polynomials don't do this. Rational functions do this, all right? And so they allow us to model, again, other real-life things that behave this way. You could replace this with this survival rate. You could replace it with the probability that that a light bulb is going to work, right? You go in, you buy a brand new light bulb, you put it in, and then over time you expect it's going to work. But there's a lifespan for a light bulb, right? And at some point it's going to die, but you can't say exactly when. So just the probability drops down. Okay, here's something else that you can kind of model with a rational function. You know, people get into these health kicks and they go and they try and lose weight, right? So here's your weight, and then here's time or days or something like that. So let's say you have a starting weight, I don't know, let's just say 180 pounds, whatever. Okay, you weigh 180 pounds and you start working out, right? And so you start weighing yourself every day. So maybe your weight starts to drop, right? Now, can it be a linear drop? I mean, maybe for a little while, but what's going to happen eventually if it's linear? Then you're saying at some point you're going to weigh 0. I mean, right? Because you'll hit the x-axis, and that just, I don't care how much you work out, you're never going to like work off your bones, right? I mean, that's not going to happen. So there is some weight here. Okay, I don't know what it is. It's probably different for every person, but there is some weight that you just can't ever get below that weight. So this would be like your horizontal asymptote. And it's going to drop, and then you're going to kind of sort of like plateau. That's what I think in the workout world they call it plateauing, where you're plateauing. You're hitting this floor that you just can't seem to get below, right? Polynomials won't work for that. Quadratics, right? Lines, none of those work. Rational functions, really good for this. Okay, questions? So let's see what rational functions look like. Do you remember that ugly definition I gave you last class for a polynomial? I said a polynomial looks like this: a sub n x to the n plus a sub n minus 1 x to the n minus 1, blah, 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 and it was real ugly. Remember that? Okay, so a rational function looks like this. f of x equals n of x over d of x. Now, what the heck is that? Okay, this here is a polynomial, and this here is another polynomial, and you're dividing them. So you're taking one of these and dividing it by another one of these, and they are different. They're not the same polynomials. And so I call this n of x and d of x. Why do you think I called it n and d? Numerator and denominator. So this is like your numerator polynomial and your denominator polynomial. If you take two polynomials, divide them, you create a rational function. All right, so let's look at some examples of specific polynomials. Specific rational functions. How about this? Is that a rational function? Is this by itself on top a polynomial? It's linear, but remember I told you all linear functions are polynomial functions? Right? That's a first degree polynomial. So that is a polynomial. Is that a polynomial? Yes. So is that a polynomial over a polynomial? Yes. It's a rational function then. Another example. X squared plus 4x over 3x minus 5. Is that a rational function? Yes. You have a quadratic function on top of a linear function, but these are both polynomials, so that qualifies. Let's look at something else. Let's change this right. I got to be real careful here. Let's just make that 2x minus 2. There we go. Is that a rational function? Yep. Polynomial on top, that's linear, over a third degree polynomial on the bottom, right? So all of these are rational. What's that?
X plus 3, you factor it out. That's the difference is squared.
Yeah, we're actually going to, I think we're going to graph all three of these. Now, whether or not we'll be able to do, well, we should be able to do it today. But it might take us the entire class to graph these three functions. All right. Do you have an idea of what they look like? Yes? Question? What's up? No? Just not happy about this? Okay. All right, so that's what rational functions look like. And now let's go about trying to figure out how to graph them. All right? We already know that we might have this like horizontal dotted line that pulls it down and like it goes towards it, right? These do not have to have them though. They can, but they do not have to. The rational functions are kind of weird. It's, you know, in the polynomials, the left and right was like up, down, we could figure that out, and the middle was a question mark. Right. For rational functions, like almost the entire function is a question mark. There's so many different combinations of what can happen, it makes it a lot more difficult to graph these. All right, so we're just going to have to kind of play with it and see what happens. All right, so we will graph those. Let's start out with this one. Now, I want to put a big asterisk here just so you understand. This first one that we graph, the way I go about doing it right now is not the final approach to how we're going to graph these. It's because it's our first one, we have to think some things through first. And then from here on out, we will just kind of use a little shorter, like shortcuts to get to the same result. All right? So follow me through this first one? Yeah? Okay? All right, so what were some of the things that were of interest to us on all graphs that we've done up to this point? What are some things that we always went and looked for? X-intercepts, y-intercepts, right? For lines, we always had x-intercepts and y-intercepts. For parabolas, we usually had x-intercepts. We always had a y-intercept. On polynomials, didn't we like set the function equal to 0? Yes? So x and y-intercepts have always been part of what we do, right? So let's try that on this one. X-intercepts. What are they? Well, how do we find the x-intercepts for functions? We set it equal to 0, don't we? Okay. Now that equation might look, might look scary to you, right? Like, it may look like, whoa, what do I do with that, right? But I've got good news. With all rational functions, you can always multiply by the denominator on both sides. See, I have x plus 3 here. I can multiply it here and here. Now, when I do that, this cancels, right? And what's 0 times anything? Just 0. So isn't this just going to turn out to be x is 0? Just that, x equals 0? And that works for every rational function. When you set it equal to 0, at the end of the day, it's just going to be setting the top to 0. Okay, let me say that again, because I told you we're going to have shortcuts. When we go to find the x-intercepts of a rational function, all you're going to need to do is set the numerator equal to 0, and that's it. Okay, I'll write the steps down later, but that's going to be one of them. Find the x-intercepts by setting the numerator equal to 0. So we have an x-intercept here, don't we? Yes? Okay, so let me go to a graph. Right now, here's what I know. And that's all I know, right? That's all I know. Now, there's something else happening with this that never happened in any function that we ever looked at before this. It's a problem spot. It's an actual value of x that I cannot plug into the function because it causes a problem. Does anyone see what it is?
-3.
X is -3. Do y'all see that I have a problem if x is -3? I'll go -3 plus 3, right? Which will be 0, and I'll have division by 0. And we're not allowed to divide by 0 ever, right? Ever? So we have this weird thing happening at x is -3. So I'm going to put here, notice that x cannot be -3. Again, I'll have a more formal process for this in a second. But I want you to notice that it can't be. So if I go to -3, on my graph, there is no graph here. It's impossible. Like when I plug in a point, I can't plug this point in, right? Which means I can't draw a dot anywhere. So what I'm going to do, and I'll do it in a different color, is I'm going to put a dotted vertical line, which is going to remind me that nothing can be plugged in at -3. Can I plug in -4? You can plug -4 in here, -4 in here, and you get a number, wouldn't you? Can I plug in -2? Sure. Can I plug in 0? Yeah, if I plug in 0, what do I get? 0 over 3? 0 over 3 is 0. So I can plug any value in except -3. So I should have graph over here, I should have graph over here, right? But at -3, I should not have anything. Now that's important because that means that when you draw it, you have to at some point pick up your pencil. Right? If I'm drawing something over here, whatever it looks like, I have to pick up my pencil and not draw anything here and then draw something over here. So we actually have a break in our graph, which is the first time this has happened. Lines, we could always draw. Parabolas without picking up our pencil. Polynomials without picking up our pencil. All right? So at this point, we're kind of in an interesting situation. We're kind of in an interesting situation because I'm not quite sure what else we can do to draw this, right? I'm not quite sure what we can do. So let me recommend we try something. Why don't we just pick a point over here? I'm going to put a little x here. I'm not going to put a dot. Let's just pick a point that's over here somewhere. So someone give me any point over here. -5. First thing I heard. Okay. Now, that point, I'm going to call that a test point. And you'll see what we're going to do with it in a second. Now give me something between this vertical dotted line and this dot. Any number in here. -1? Okay. That one. Now something on this side of this dot. Anything over here? 2? Okay. There we go. So what I have here are what I'm going to refer to as 3 test points. All right? And what I'm going to do is I'm going to plug these values into my function and see what it spits out. And that's going to give me a little bit more picture, right? Because I'm going to be able to draw some dots here. Okay, let's do it. What would f of negative 5 be? So let's plug negative 5 into this. We get negative 5 over negative 2, which is 2.5. Y'all agree with that? 2.5. So that means if I go to negative 5 and I plug that value into the function, it spits out a positive number, 2.5, right? Which means it's up here. Okay, let's do the same thing for negative 1. What do you get here? Negative 1 over negative 1 plus 2, or plus 3. So negative 1 over 2. So negative 0.5, negative 1/2. So at negative 1, I actually have a dot that's down a little bit, don't I? I'm just going to put a dot here. And then what's happening at 2, if you plug in 2? So f of 2, you go 2 over 2 plus 3, 2/5, which is 0.4. So at 2, I'm up a little bit, right? Like this. Y'all okay with this? So now at this point, do not draw anything, okay? I'm gonna start to kind of get you to think about what's happening here. Would it be safe to assume that this probably connects, these 3 dots probably connect just like that? It's probably safe to assume that it does something like that, right? The question becomes, what's the right-hand behavior? Like, what does it do? Does it go up here? Does it go down? Right? Does it flatten out? Like, remember the horizontal asymptote? Does it go towards something? We don't know, do we? Now, I can say this. Can it come back down? Can this go like this and come back down? Just let's draw that. Could that happen? I'm hearing some yeses, but I challenge you to think through that a little bit more. Is it possible for this graph to go and turn back down over here? Why not? What is this right here? What is this point on the graph right there? That's an x-intercept, isn't it? And I only have one x-intercept, right? The only x-intercept I'm supposed to have is 0. So this graph cannot physically turn back down on itself because I create an x-intercept. So that going down cannot happen, which means one of 2 things has to happen. It either turns up and keeps going up forever, or it flattens out to some horizontal dotted line, like the survival rate for something. Okay? I don't know yet, but it's got to be one of those 2. Now, more interesting is what's happening as I try and draw it this way. So can it do this? Could it turn back up like that? No, because that would create an x-intercept, right? So I can't do that, which means that it's going to have to somehow maybe go down. Can it go straight across? Why can't it go across? Because this dotted line, I'm not allowed to, right? So this vertical dotted line that I found, it actually has a name. It's called a vertical asymptote. Didn't we just talk about a horizontal asymptote? This is a vertical asymptote. And the vertical asymptote has the same effect, but it's vertical. So what happens is, see, I'm trying to draw my graph to the left. And I can't turn back up because I'm not allowed to cross the x-axis because I only have one x-intercept. So I must go down towards that dotted line. I can never actually touch it, but it's kind of like what we did with the survival rate. If you turn your head, it's doing that this way. Do y'all see that? Okay, let's continue to try and draw. This right here, remember, was a big question mark still, right? We didn't know. This we kind of connected the dots, and then over here we said we couldn't turn up. There's kind of like this barrier here. It's going to just force us to go down. Now, go to this point right here. What about to the left, if I try and draw it? Can it come down? No, because it would cross the x-axis. Yes?
if it goes down, can you just have a horizontal asymptote? So like, it could go down as long as it doesn't touch the x-axis?
Horizontal this way?
Yes. So like, if we draw a line downward, as long as it doesn't touch the x-axis, it could go down, right?
Like you're saying, like, it's like that, the one that never touches the graph.
Are we talking about this point right here, or are we talking about this?
So, I mean, like, going down as a line.
Like this? Oh, you mean this way without touching it? It could do that, yes. I don't know if it does, though. What I'm saying is, can it come down and go across the x-axis? Sorry. Can it come and do this? No. Okay. So could it come and flatten out to something? Yes. Could it just go up forever? Yes. So just like this end, I didn't know. This end, I don't know. Yet, we will have a way of getting it. But what about drawing this dot to the right? Can I, see, I can't cross this, right? So can I come down over here?
Yes.
Well, if I come down, won't I cross the x-axis? Right? I can't do that, which means it has to do what? Go up, like this. This is a weird-looking function, isn't it? This -3 right here creates this like blowing up of your function, almost like a volcano. It just goes up, right? Then over here, it's like diving down. That's all because of that division by x plus 3 creates this weird thing, all right? All right, so just a quick recap, because I know this is a lot. When you have a rational function, if we want to find the x-intercepts, what do? Numerator is 0. If we want to figure out anywhere where we have these dotted lines that create this diving effect of our function, what do? Not the numerator. We set the denominator, because remember, we got -3 from this, didn't we? So if we set that equal to 0, wouldn't we have got that number? Okay, say it again. To find the x-intercepts of a rational function, we set the numerator equal to 0. To find the vertical asymptotes of a rational function, we set the denominator to 0. How do we find the horizontal asymptotes of a rational function? I have not told you. And that's what I'm about to tell you, okay? Y'all got that? All right. We'll do a few of these, and I'm really hoping it'll start to resonate a little bit. I'll get rid of that. So. How to find horizontal asymptotes of a rational function. Okay, here we go. I'm going to give you the process on how it is that you will find. You remember these question marks? We didn't know if it flattened out, right? Does it flatten out at the ends? To do that, to find the horizontal asymptotes of a function, of a rational function, here's what you do. Compare degree of nx with dx, d of x. What is that saying? What the heck am I saying there? I'm not sure I even understand what I wrote. So let's go back and look at the function I just gave us. There's our function, right? When I say n of x, I mean the numerator, don't I? And when I say d of x, I mean the denominator. I want to compare the degrees. I want to compare the degrees of those, because aren't the two separate things polynomials separately? What is the degree of the numerator here?
1.
Okay, what is the degree of the denominator? 1. Okay. They're the same, aren't they? They're the same? For this particular problem, they're the same. But what could happen? If I just give you two polynomials, tell me the possibilities of what could happen. The degree